Might just grab some water. Yeah. Is there a bathroom? There's juice and stuff, Matthew. I just wanted to rinse
over there, like just behind the stairs.
Yeah, I don't know what we're doing outside. You come here.
3 times over 3 years.
So good. So is my camera, can they see me or
should be able to see you?
let me just, oh yeah, I've got my video running.
Yep,
that's good.
Yeah. All right.
Awesome.
Okay.
I might just stop that and where is it? No. Okay.
All right. Okay, everyone, welcome to the afternoon session. So for our first talk, we're going to have Professor Matthew Bales, and he'll be talking to us about relativistic adventures with pulsars.
Okay, thanks very much. And for those of you who don't know me, I'm Matthew Bales. I'm a pulsar and radio astronomer, and got a funny echo. Is that me? How about that? Is that better? Oh, whoops. No, that looks better. Okay. Sorry, I'm a radio astronomer. I mostly do radio pulsar work, but also I've been quite interested for the last 15 years or so about fast radio bursts. I'm also the director of OSGRAV, which is our national ARC Centre of Excellence. And I'm sorry I can't see the people online, but it's nice to be talking to some new faces. So let me just click here and hope this is going to work. So this is a talk I'm giving, which is going to just go through a little bit of how I got interested in relativistic gravity and some of the things that we've learnt mainly from radio pulsar work. So I'd just like to start by acknowledging the Wurundjeri people of the Kulin Nation, who are the traditional owners of the land on which at least those of us in Melbourne are on, and pay my respect to their elders past, present and emerging. So I'm quite old now. I was born 60 years ago, and on the same day as the quasar was published in Nature, which meant I must have had to be an astronomer. It's a shot of me in Alice Springs trying to cool down. I became interested in how the universe worked at a very young age. My nickname at primary school was the Professor, which everybody thought was a great derogatory term except me, and I used to beam with pride. And one day when I was crossing Glenburn Road, which was the way to school, there was actually a pedestrian traffic light way down the road, and you could take an extra 5 minutes to get across the road by going and using the pedestrian crossing, or you could risk crossing the road by foot. And when I was 6 years old, I thought this would be a good idea. And I remember looking at the cars that were coming towards me, and I wanted to know why we could see them, because I thought maybe if they were invisible or something, every now and then you might die, and I wasn't keen to do that. So I asked my teachers at school, why can we see the cars? And I asked my parents, and none of them had any idea really. They didn't know about photons or how eyes focus light and stimulated optic nerves and electrical impulses to the brain and so on. So I was very frustrated at primary school that I didn't really understand how the universe worked, and I really wanted to understand it better. And so I ended up on a course of discovery that I'm still undertaking to be a physicist. So I ended up back in 1984 at the University of Adelaide, and I thought astrophysicist sounded cool, and I ended up being given a paper by my supervisor, Peter Zekras, whose father actually has a coordinate system in general relativity named after him. And he handed me a paper on the binary pulsar. So this was 2 neutron stars going around each other every 7 3/4 hours. And remarkably, because the system was so relativistic, every orbit, the system was shrinking by 3.1 millimeters. Now, you might think that something that's 20,000 light years away and shrinking by 3 millimeters would be very difficult to measure, but we could. And in fact, Joe Taylor, who by coincidence ended up marking my PhD thesis, wrote a very important paper that showed that these 2 neutron stars were exhibiting a whole lot of relativistic effects. And because of that, they could measure the total mass of the system, and they could predict the various other relativistic effects like time dilation and gravitational redshift, and predict that indeed the orbital period should change by such that the orbits were going on these slightly smaller trajectories. And because it was doing 3 orbits a day, the cumulative effect of this meant that the system was getting back to periastron a little bit later. And back in 1984, the prediction, the GR prediction, I hope you can see my cursor, was still fairly mild. And my supervisor wasn't really the sort of person that kept up to date with the literature. So he actually handed me a paper from 1978 when the effect was really quite marginal, and said to me, how on earth can you get 2 neutron stars going around each other? This will be the subject of your honors thesis. So this is how I got into neutron stars. It's quite remarkable how accurately you can measure things using radio telescopes and pulse profiles. So the orbital period of the binary pulsar is 7.751938773864 hours, which is a remarkable number. The orbital eccentricity, so this is the classical Keplerian parameter, is 0.61713334. The total mass is about 2.8 solar masses. And we have this shrinkage of the orbit, which, because it's has a very clear prediction from general relativity, actually led to the Nobel Prize for Joe Taylor about 9 years after I started working on this system. And ever since, people have been timing this pulsar, and the GR prediction, which is this kind of parabolic line, and the experimental points are remarkably in agreement. And so Russ Holst, who's the student who discovered this pulsar, and his supervisor who timed it, along with people like Joel Weisberg for many years, were awarded the Nobel Prize, although Joel sadly was not. A lovely man, so a bit sad about that. So this is how we kind of think of a pulsar. It's a neutron star, which is typically about 1.4 times the mass of the sun, but its diameter is probably a little bit over 20 kilometers. And the idea is that it has a very strong magnetic field. And because it rotates, if you grab a magnet and rotate it, you don't actually feel much of a force. That's because a fridge magnet is of order 100 Gauss. But if you take a 10 to the 12 Gauss magnetic field and you spin it many, many times a second, it actually screams in pain and gives off this relativistic particle wind, which generates radio emission. And that radio emission is emitted in like a lighthouse beam. And if you get a big enough radio telescope and point it in the sky, you can actually see these pulses coming from the heavens. And every rotation, you get a pulse. So you might wonder how you can get 1.4 solar masses of neutron star into something only 20 kilometers across. Well, just to give you an idea of something we're used to the diameter of, the circumference of the Earth is actually 40,000 kilometers. And in fact, the meter was originally defined by the French such that there would be 10 million meters from the North Pole to the equator. And that's why the circumference of the Earth is 40,000 kilometers. But the Earth is actually quite small by galactic standards. If you look at Jupiter, Jupiter is quite a lot bigger than the Earth, not as dense, mainly because it's able to retain the hydrogen that helped form it. But if you compare Jupiter to the Sun, it's actually quite small. The Sun is actually not a particularly large star. It's kind of what you might think of as a median star in our galaxy. But there are stars that are 10, 20, maybe even 100 times as big as the Sun. And so the types of pressures that you get at the center of such objects is quite extreme. And when they've burnt all their hydrogen and helium and made all their way to iron, the central cores of these stars gets about the same diameter as the Earth, but it's made of very heavily compressed iron, and it collapses in less than a second once the pressure gets to a certain critical value, and you end up with a neutron star, which is about 500,000 Earth masses, but only 20 kilometers across. So in the what was called the binary pulsar, when it was first discovered, it was the first neutron star that was going around another neutron star that was a pulsar, was discovered. It was a little bit of a mystery as to how on Earth you could get two neutron stars going around each other. And the typical separation here is only like a few times the radius of the Sun. But we know that stars that are 10 times heavier than our Sun typically have radii that are more like 10 solar radii. So there must be some interesting physics that leads to such a tight system. The other thing that's interesting about the system is it's shrinking by 3.1 millimeters in orbit. And so you can easily do an extrapolation into the future and work out that eventually the orbit will shrink to the point where the two neutron stars will merge. And in this system, the timescale is about 300 million years. But we know of other systems now where the timescale is only more like 80 million years. And indeed, using the LIGO interferometer, we've actually seen two neutron stars merge, and we'll get onto that in a minute. So using the LIGO gravitational wave observatory, you can take signals from the LIGO and Livingston detectors, combine that with Virgo. And if you detect a gravitational wave, you get an error box on the sky, and error boxes can be quite large depending on which detectors we're on and the signal to noise ratio and the wavelength, if you like, of the gravitational wave, which is how fast they're going around each other when you detected it. And you get these error boxes on the sky. And for most of the black holes, they're very large and they're difficult to see. Because the neutron stars travel around each other much faster when they're coalescing, the kind of wavelength of the gravitational wave, if you like, is much shorter. And from a kind of lambda over d thing, the error boxes are much smaller. And indeed, when we saw the first neutron star merger, which was GW 170817, it wasn't seen in the Virgo detector, which was because it was at an antenna null for that detector. It was in the two LIGO detectors, and it was able to be localized to only about 20 square degrees. And it was less than 24 hours later that the optical star associated with that, what we call a kilonova, the destruction of these two neutron stars, was shining in a way that many, many telescopes around the world could see. So when 1708-17 went off, the optical astronomers went to the nearest galaxy catalogs, and there were about 1 million galaxies within the distance of 1708-17. This is what's called the 60F Galaxy Redshift Survey. It's a sort of southern hemisphere collection of galaxies. You can see some of the galactic structure, and each one of the dots in this represents a galaxy. And all we had to do was work out which of these galaxies had had the neutron star merger. Because of the error box being quite small, it didn't take long to do a mosaic of the relevant areas, and 6 different groups within 2 hours of each other all managed to identify the correct host galaxy, which was this green one here. It's quite, nicely marked. And this was the Hubble Space Telescope image. It's what's called an elliptical galaxies. These are what's called red and dead galaxies. They don't have a galactic disk to form stars. They're all sort of mixed up, and so they don't get the sort of pressures required to have active star formation at any significant rate. And the neutron star merger was way out here in the kind of outskirts of this galaxy. And we don't know whether or not it was ejected from the center of the galaxy, or just has always been out there, or was part of a globular cluster system and merged in its core. Unfortunately, this system is so far away that you can't detect globular clusters, which is quite sad because it's only 40 megaparsecs away. So how do these systems form? Well, you get a big star and a little star, and the big star and little star kind of chat, and the little star says, if you keep burning all your hydrogen so quickly, you're going to end your life rapidly. And so the big star ends up becoming a giant and blows up. It transfers some of its mass to its companion, and then eventually it blows up. And when it does blow up, it leaves behind a neutron star, and the neutron star goes into an elliptic orbit, partly because there's been a lot of mass loss from the system, and partly because it probably received some sort of asymmetric kick velocity. And if I just pop on the trail, you can see that we end up with this highly elliptic orbit. It might have an orbital period of a year or more. And there is a well-known system we'll see in a minute called 1259-63, which is actually a neutron star going around a massive BE star. And it has an orbital period of about 3.5 years and a highly eccentric orbit of about 0.8. So these systems are very gravitationally stable and don't evolve much during the initial lifetime of the neutron star. The neutron stars don't actually live very long. Typical pulsar only lasts for about 1 million years, whereas it takes a B star more like 10 or 50 million years to leave the main sequence, depending on its mass. But eventually all good things come to an end, and the companion star swells up to become a red giant. And when it does, the neutron star, when it's at periastron, can scoop matter off the companion and end up as an X-ray source. It forms an accretion disk, and that disk does two things. It destroys the magnetic field of the neutron star, and it also causes it to spin up rapidly until it's spinning at maybe a few tens of hertz. So we can see how that works. The star, it's not super accurate here, but imagine that this thing is filling its Roche lobe. To talk to the animator here. But the material tries to fall onto the neutron star. It ends up colliding with other material that's already present in a disk, and that heats it up. the temperature can exceed 1,000,000 degrees of the accretion disk. And because it's rubbing against itself, it gives off energy. That energy means it can get closer to the neutron star, and the material spirals in until it gets quite near the surface of the neutron star, where magnetic forces can grip the charged particles and funnel the material to the polar caps of the neutron star. So you end up with an X-ray system. And if you actually grab an X-ray telescope and you point it at the heavens, you don't see anything because of our atmosphere. But if you put an X-ray telescope outside our atmosphere and you look at our galaxy, you can actually see a few hundred of these systems that are currently accreting. The very high mass ones are called high mass X-ray binaries, and the ones with low mass companions are called low mass X-ray binaries. And the high mass X-ray binaries don't live very long because the mass transfer is unstable from a more massive body to a lower mass body, and the orbit starts shrinking, which means the mass transfer happens even more rapidly, and the neutron star ends up disappearing into a common envelope in the system. The low mass X-ray binaries, however, when they transfer matter, the orbit widens, and the mass transfer phase could potentially last for 1 billion years or so. And that's long enough to cause the neutron star to spin all the way down to almost a millisecond rotation period. So depending on your orientation of this system, if it's what we call edge on, when the neutron star goes behind its companion, you actually get an eclipse. And so you can learn something about the orientation of the system if it eclipses. If it's more face on, then you don't have an eclipse and you see the system throughout its orbit. We've only seen a few rotations, but these systems typically orbit tens or millions of times before the mass transfer ends. And when it does, we end up with a neutron star that's very rapidly spinning. We call that a recycled pulsar. And the speed at which it's rotating depends on the mass of the companion. If you've got a very heavy companion, maybe you only get spun up to 10 hertz or so. If you've got a very low mass companion, you can go all the way to about 700 hertz. So eventually this mass transfer stops, either because the neutron star has entered the envelope of the star, or in a low mass X-ray binary, it just eventually runs out of material. If that happens, you end up with a white dwarf and a spun up pulsar. In the heavier systems, it's a little bit more exciting. The neutron star gets an orbital friction associated with passing into the common envelope of the star, and it spirals in, expels a whole lot of matter, and you end up with a very tight binary system where you've got this rapidly spinning pulsar around a star that's about to blow up. And when it does blow up, you end up with the two neutron stars going around each other in an eccentric orbit. And we see the first one of these was discovered in 1974, led to the Nobel Prize. Since then, there's been about another 13 or 14 discovered, I think only 10 of which are published. But there is one system where, at least for a brief time, we could see both of the neutron stars. And I'll get onto that a little bit later. So over millions of years, these systems get closer and closer to each other, and eventually they radiate so much gravitational wave energy that they coalesce, and we get a neutron star merger, like 1708-17. So this is the Parkes telescope. It's slightly on the wrong scale here, but it is a few hundred kilometers to the west of Sydney. What this animation is supposed to show you is that in the sky, there's lots of things flashing, but the telescope only looks at a very small part of the sky and only sees typically less than a square degree of the sky at once. And this is why we don't detect thousands of fast radio bursts a day. We only see maybe one every 10 days with the Parkes telescope. And that's because we only see a very small part of the sky. So a fast radio burst is a typically millisecond flash of radiation, and it's a very hot topic in radio astronomy. But today I'm going to spend most of the time talking about gravity and neutron stars, and sadly fast radio bursts don't seem to have many attributes that would allow you to study relativity. So I went on to work on trying to measure the speed of pulsars for my PhD. I used the Parkes and Tidbinbilla telescopes together, and you can do something called very long baseline interferometry. And this enables you to measure the position of a star down to less than 100 milliarc seconds. And if you wait a year or two, you can actually see them moving across the sky and learn about their velocities. Neutron stars are unusual in that they travel typically 100 to a few hundred kilometers per second, whereas a normal star in the galaxy only goes sort of 10 to 30 kilometers a second. So there is obviously something that happens to a neutron star either at its birth or shortly afterwards that accelerates it up to these very high speeds. This is what's called the BP diagram, where B is magnetic field strength and P is the period. You get a rough handle on how magnetic a neutron star is by taking the square root of the rotation period and the period derivative. And you end up with these different regimes in this diagram of magnetic field strength and spin period. This area here is called the pulsar island. It's where most pulsars live, and most of them are fairly boring. We think neutron stars are born spinning a little bit like the Crab pulsar, which is going at 33 milliseconds. It rapidly spins down and joins the sort of pulsar island within about 100,000 years. After a million or few, neutron stars tend to sort of burn out, and we can't see them anymore as radio pulsars. But if they have a companion star, they can be recycled and both moved down to shorter periods by the accretion of angular momentum, but also their magnetic field strength is reduced. So depending on how heavy your companion is when it blows up, you either are left here, which is sort of the area of the neutron star binaries, or if the neutron star has a very low mass companion, you can end up all the way down to with a spin period of less than 2 milliseconds. So we're going to learn a little bit about these systems down here and how you can use them now. So when I was a postdoc, I spent a lot of time trying to find pulsars, and these globular clusters. These are sort of relics of initial formation or star formation in our galaxy. They typically have 100,000 to 1 million stars in them. And this particular object that we discovered was a very long rotation period system in a globular cluster. And if you go back to this slide here, and the idea is that if you're in a globular cluster, there was only one wave of star formation maybe 10 gigayears ago, and most of your long period pulsars should be dead. But this one was unusual in that it was rotating quite slowly and still alive, and it had a high magnetic field. And back in '93, a lot of people thought magnetic fields just decayed spontaneously, and so it's quite unusual to find a high field system, or at least according to theory, and this ended up being a Nature paper. We also did an all-sky survey with the Parkes telescope looking for these millisecond pulsars. And it was actually Duncan Lorimer was the first person to see this candidate. When you do these pulsar surveys, you basically take filter bank data, which is basically the radio power as a function of frequency and time. You do all sorts of Fourier transforms, and you end up hopefully discovering interesting systems. This particular system was incredibly bright. It's called 0437 minus 4715. It's the nearest neutron star we know of to the sun. And it was so bright that it actually broke our radio frequency interference rejection algorithm, because we decided a priori that if any system appeared more than 6 times in different pointings, it couldn't possibly be real. And so we deleted it. And luckily there was another bug in our system, which meant that the deletion software wasn't working properly. And so we ended up discovering this system, which was, I think, the subject of about 6 different Nature papers. So that was that was a very good case of a double bug. This was one of those Nature papers by my first PhD student, John Bell. And you can see this little kind of bow shock thing down the right-hand side. This is an inverse video system. And that black dot there is the white dwarf companion to the neutron star. The neutron star is not visible in the optical, but this photograph was taken by Andy Fruchter with a 4-meter telescope with an H alpha filter. And the velocity of the neutron star is in this arrow, and you get this beautiful bow shock. So this is the relativistic wind of the neutron star pushing the charged particles in the interstellar medium and forming this nice bow shock. So this is another system that we have worked on. Whoops, where is it? I think I've actually played with the input parameters on this one, and it's not as accurate as it could be, but there are some neutron stars that are going around white dwarfs where the neutron star blew up after the white dwarf was formed, and you end up with these eccentric systems. However, that was not the system. So this is an example of a main sequence star with a neutron star going around it, and as an example of a system I showed earlier in the animated binary evolution tree. And this is the first time a neutron star had been discovered going around a main sequence star. Because the system was kicked out of its orbital plane, its orbit was wobbling in a way that was easy to determine from pulsar timing. And we wrote this Nature paper with Vicky Caspi about how this neutron star must have received a kick in order to be exhibiting the orbital characteristics that it had seen. Most of the neutron stars are much heavier than their companions. And about 10 years ago, we discovered a system that had almost completely destroyed its companion. The system was only about 1,000th of a solar mass. And so this was a little degenerate object orbiting a pulsar. And one of my friends suggested that maybe we should call this a planet. And then because we looked at its chemical composition and radius and deduced that it should be made of carbon, we decided to call it a diamond planet. And if you call something a diamond planet, you become an international media sensation. Whereas if you just say you've discovered a carbon remnant of a star, you don't. So this is a very interesting example of marketing. How am I doing for time? Okay, cool. So we called this system a diamond planet, and a lot of people found it quite interesting. Whether or not it's made of diamond or not is a moot point. But this system only has an orbital period of a couple of hours, and it was discovered with the Parkes telescope as part of the High Time Resolution Universe survey. So we've done a lot of surveys with the Parkes telescope over the years. It's probably getting a bit old now, and there's a limit to how many times you can upgrade a telescope before you run out of collecting area, and you hit various fundamental limits, although the very clever engineers at CSIRO have just developed something called a phased array feed, which should increase the sensitivity of the telescope and its collecting area, or the area it covers on the sky, by a factor of 4. So if you're interested in doing pulsar surveys, talk to me afterwards, because I think this system is possibly going to discover a whole lot of pulsars when it finally works. We discovered a pulsar called 1909 -3744 using the Parkes multi-beam system with Brian Jacoby and another Swinburne student, Russell Edwards, discovered a large number of pulsars that are mainly part of what we call pulsar timing arrays now. So you can do some cute tricks with these millisecond pulsars. You can measure when the pulse arrives at the telescope very accurately, in fact, below a microsecond. And if the white dwarf goes almost between you and the pulsar, you get what's called the Shapiro delay. Because there's more measuring rods in the vicinity of mass than there are without it, there's this characteristic cuspy kind of delay, and it's a function of the orbital inclination angle and mass of the companion. And in this system, 1909, we were able to measure both the amplitude of this time delay and its shape, and that gives you the mass of the white dwarf. You can then use the mass function to determine the mass of the pulsar. And at least when we did this, this was quite a novel breakthrough because there were very few millisecond pulsars with known masses. Just to give you an idea of how accurately you can measure things in these systems, this particular system is going around a white dwarf about every day and a half. The orbital eccentricity is, I think, 10 to the minus 7. And although the semi-major axis in the system is 569,000 kilometers, the difference between the semi-major and semi-minor axis is only 3.7 microns. So you really can make some astounding measurements, and that will become useful later on in this talk. So we've also been doing other pulsar surveys and finding mainly kind of boring slow pulsars, but there is the odd millisecond pulsar still being found. Unfortunately, as pulsars get fainter and fainter, the number of applications you can apply to them reduces with the same telescope. So you need to build bigger and better telescopes, which is why we're building the square kilometer array. So I just can't remember exactly why I've got the system in here, but it appears that the mass ratio here is about 10 to 1. So this is a millisecond pulsar system with a white dwarf companion. And the next slide will reveal why I was going to talk about this. Oh, and that's because most of the millisecond pulsars we know about have a binary companion. Roughly 75 to 80% of them have a white dwarf companion. And you can use when the pulses arrive to try and detect the passage of gravitational waves from supermassive black holes. And this was a paper written by Ryan Shannon some years ago, which showed that the amount of gravitational waves present in our data, we could put a limit on that, because if there were tons of supermassive black hole binaries, space-time should be being compressed, and this should be leading to an anomalous noise, which we weren't seeing in our data. Other applications of pulsars is you can measure the mass of them. And if you have a friend using the NICA instrument, which is an X-ray telescope, they can model the radius of the neutron star if they know the distance. So this pulsar 0437 that I mentioned before is really bright. It's had its mass determined, and also the distance to this pulsar is known to better than 1%. And so this is very good for learning about the mass and radius of neutron stars. And in order to understand the inherent properties of a neutron star, how squishy it is, there's a thing called the equation of state. There's a whole bunch of them. And what we're trying to do is work out which of them could be correct. And so our particular pulsar, we know its mass to about a few percent accuracy. And we're waiting for the NICA folks to tell us the radius, and then we'll get a constraint and we'll be able to rule out various equations of state of nuclear matter. Lately, we've been commissioning a new telescope in South Africa called Meerkat. It actually consists of 64 of these dishes, which are about 14 meters effective diameter. And Ryan Shannon at Swinburne is leading a millisecond pulsar timing program where we basically look at 89 millisecond pulsars and try and measure this galactic or this gravitational wave background that may be caused. Meerkat makes these amazing pictures of the sky. This is the galactic center. And you can see there's all sorts of exploded stars with bright things in the middle of them. If you look really carefully in the background, you can see these things that are actually distant radio galaxies. There's a supermassive black hole there squirting out a jet. And there's these weird filaments that nobody really knows the origin of, but they just wave their hands and say magnetic fields and stuff in the vicinity of the galactic center. This is only the inner kind of few degrees of the galaxy, but it's a remarkably beautiful image that the Meerkat people put together. The reason they could make this map so well is that they have 64 antennas in their array, whereas previously to look at the galactic center, you either had to use the VLA, but it was way down on the horizon, or you had to use the Australia Telescope Compact Array, which only has 6 antennas, so you don't get very good spatial makeup of it. So the Mir Time program is observing over 1,500 pulsars with Meerkat. I'm most interested in the relativistic binaries and the millisecond pulsars. When you actually look at the two of these neutron stars going around each other and you plot the amplitude of the radio pulse on the x-axis here and orbital phase in degrees on the y-axis, this is what the pulse looks like. It's actually a double pulse shape. And you can see that you get these kind of tiger stripes appearing. And the reason they occur is because you have the radiation from one pulsar shining through the magnetosphere of another. And when the magnetosphere of the slow pulsar rotates, it blocks the radiation, but only at particular rotation phases. So roughly every 2.7 seconds, you get a burst of radiation coming through. Was it every 1.3 seconds? I can't remember. It's either half the period or double it. And so we've been using the Meerkat telescope to study what happens when radio waves travel through a magnetosphere of another star. This is another way of looking at this is the total power received from the bright, what's called the A pulsar, the rapidly spinning one, as a function of orbital phase. And you can see that it starts getting eclipsed and then gets solidly eclipsed and then comes back on again once it goes past. And there's something weird about the radiation in that the amount of circular polarization gets higher than what the linear polarization used to be when the system is right in the middle of the eclipse. It was quite nifty. And we're using this to understand the orientation of the B pulsar and hopefully be able to demonstrate that it's precessing due to spin-orbit coupling in the system. And that's what this is supposed to show, but as the violin plot's a little bit dodgy, you could probably do a straight line through this. I think the purple is the GR prediction. And we've now got another 600 days and we'll be writing a paper on this soon. There is another system where a neutron star is going around a white dwarf. Because the neutron star received a kick at birth, it's actually not coplanar with the spin of the white dwarf. And this gives rise to a relativistic spin-orbit coupling. And I had a student, Vivek Venkat Raman Krishnan, who managed to deduce the mysteries of this pulsar by timing it for 20 years. That wasn't the length of his PhD. He came along at about year 17 mark. And for many years, we actually struggled to understand what was going on here. But then he realized that the orbital orientation of the system was changing. And because of that, we could deduce that spin-orbit coupling was actually in play. And it led to the whole space-time in the system is being rotated because of lens-steering frame dragging in the system. So, Well, my screen is frozen, so that probably means I should stop at this point and take questions. Thanks. Sure. It's 1141 minus 6545. And the original paper on it is Caspi et al. And the last one on it is Venkat Raman Krishnan et al.
Any other questions? Yeah, sure.
So you mentioned that the orbit, the entire orbit was processing, but I would imagine that the bulk of the angular momentum is in the orbit. It has much higher moment of inertia than an individual star does. So I would have expected that the orbit would therefore stay pretty much aligned with the total angular momentum and not change very much, whereas the individual, whereas the neutron star would process a lot. But you're saying that the orbit is processing. So I'm
Yeah, so because we can measure the arrival time so accurately, because we only actually measure A sin I, we don't measure A, where A is the length of the semi-major axis. But we can measure the derivative of A sin I quite accurately, and that's what we measure. So we managed to see that the orbit was changing its orientation, and that's partly because of this lens-Thirring precession, where the tumbling white dwarf is making space-time spin in its direction of rotation. So it makes the whole orbit change its orientation. And so we can measure that A sin I. But it is true that the spin axis of the neutron star and white dwarf are also doing what's called geodetic precession, but the time scale for that is more like 400 years, I think. So for quite a long time, the spin axis of the white dwarf is roughly pointing in the same direction. And if the white dwarf is whizzing around, that makes the whole orbit kind of tilt for a little while. And then as the white dwarf precesses, it'll then sort of tilt back. So the orbital inclination is roughly 70 degrees and will stay that way, but it does this sort of little wobble with a 400-year time scale. And most of the angular momentum is in the white dwarf, but unfortunately, we don't know the spin rate of the white dwarf. So we have to sort of guesstimate it. But it's not essential for the demonstration that lens-Thirring is, but you can't deduce as many parameters as you might like because of that. But I'll repeat your question anyway.
Yeah, you mentioned that initially in the hospital concert, I was just wondering, do you know the sense of the distribution, overall distribution of pulsar, or the distribution of pulsars in general, like multi-eccentric or multi-circular?
Yep. So I'll repeat the question. So the question was, what is the orbital eccentricity distribution of the neutron star binaries? Are they mostly eccentric or are they mostly nearly circular? When the first one was discovered, it was highly eccentric. So everybody assumed they would all be highly eccentric. And then I think the next one had an orbital eccentricity of about 0.3. That was 1534 plus 12. And then curiously, a lot of them since then have actually had quite mild eccentricities, like between 0.07 and 0.2 or so. And then there's the odd one that has even greater eccentricities, like Andrew Cameron discovered one maybe 5 years ago that was very high. So it seems to be that the eccentricity, I wouldn't call it bimodal, but most of them are actually mild. And we think that's because if the two neutron stars prior to explosion, the pre-neutron star can get sort of eaten away by its companion by getting too close. And when this neutron star explodes, it's not much bigger than the Chandrasekhar limit. And you get quite a mild eccentricity induced. Whereas if they're a bit further apart, or maybe the star is a little bit heavier for whatever reason, when it blows up, it gets rid of a lot of mass and gets a bigger kick. And so I think we've got a couple that have eccentricity is bigger than a half and all the rest are lower. Whereas we had it just assumed when there was one object that everything always got a big kick and they'd all be highly eccentric. And then, you know, you get one that's low eccentricity and you think, well, that's odd. They must have had a really favorably oriented kick. And then you just keep getting more and more. And now it's like, actually, most of them don't have a big kick at all.
All right, well, then let's everyone thank Matthew again.
This guy had a question.
Oh, he did.
Sorry, I just towards the end of your talk, you were talking about the system that was kind of hard to understand the behavior needs. Like this is I don't quite understand in what sense. Is it literally that the whole binary system is facing us? What is this tumbling?
Oh, okay. So there's a neutron star and a white dwarf. If there were no kicks or anything, their spin axes would be perpendicular to the orbital plane. They'd just go around, nothing very interesting would happen. If you tilt the white dwarf spin axis by 90 degrees, and it's rotating rapidly, then it wants to make the other neutron star rotate in the same direction as the star because of lens-thirring precession. But it's quite a small effect. And so it takes some years for the orbital plane to change by much. And so the orbital plane is, we call it tumbling because it sounds dramatic, but it's really gently rocking. And because we can measure the projected semi-major axis very accurately, we call that d a sine I by dt. That's measurable. It took us a long time to realize that that might actually be changing. And because of that, it was getting absorbed into another parameter, which was the time dilation in gravitational redshift. And there's something called the mass diagram. And if GR is right, the sum of the masses gives you a straight line in that diagram, and things like the orbital period derivative give you another one, and time dilation gives you another one. They should all overlap, and in this system they weren't overlapping, and we had to scratch our heads for a couple of years to work out why.
All right. I'll join me in thanking Matthew again.